process in the computer is warming up the CPU, another process in the computer can measure the temperature of the CPU. So this seems basically pointless because there's many other ways of doing inter-process communication. There's sockets, IPC, also simply writing the files. But there are systems where there are communication restrictions on one host, generally within the military situation. These are called multi-level secure systems, and they have quite an adventurous goal. They want to ensure that no confidential information will be leaked, even when the machine has been compromised. Let's suppose that a general who doesn't know very much about computers runs a Trojan horse while he's looking at some highly secret satellite photographs. Even in that situation, these systems are designed to stop this information being leaked out. These work by giving all information a classification level, things like top secret, secret, and so on. And data cannot flow down. So if some data is top secret, it can't go to a process which is only rated for secret information. And only unclassified processes are allowed to communicate with the outside world. So even when there's a Trojan horse running at the unclassified level and a Trojan horse running at top secret level, it shouldn't be possible that data can flow from top secret down to the unclassified one. The normal ways of doing inter-process control on operating systems like this block unauthorized flows of information. So if a top secret program creates a file, an unclassified program won't be able to read it. The same with any kind of normal inter-process communication. But there is a field of research called covert channels, which tries to bypass these protections by using more unconventional means of communication. One that's been discussed a while ago was to use CPU load. So again, I'm assuming that there's a Trojan horse both at a high level and a low level. The process at the high level can use up the CPU time just by sitting in a spin loop. The process at the lower level can try to estimate the CPU load by trying to do some work of its own. If it's getting lots of CPU time, it means that the CPU is free. If it's getting no CPU time, it means the CPU is busy. The high process can then basically signal in Morse code. To send a 1, it uses lots of CPU time. To send a 0, it uses no CPU time. This was a bit of a concern for some of these systems. So they had a defense called fixed scheduling. This is where each process or each security level gets a fixed amount of CPU resources. This is similar to the technique used in real-time systems. Even if a process is not going to do any work, it's still given its CPU time slot, and that means that the process at the lower level can't receive the data. But when it's not using CPU time slot, the clock skew will change because the temperature will have changed. I don't have any of these military systems or access to them, so I instead simulated 2 completely separate computers by putting this desk lamp in one of my computers. I turned it on for 2 hours, turned it off for 2 hours, and at the same time, from the host, I made a connection to a remote computer that gave me timestamps. Now we see that the temperature changes from the desk lamp, and also the clock skew changes, as we might expect. There is a difference because now the clock skew is the inverse relationship to temperature, and this is because I'm changing the temperature of the machine doing the measuring rather than the machine being measured. For this attack to work, the attacker has to have fairly free access to the network in order to connect to this remote timestamping machine. And in high integrity systems, this is fairly unusual. But this attack can still work because a host will have multiple clock crystals. Not only is there the one that drives the system clock, but there's also one for the Ethernet controller and one for the sound card, sometimes a separate one for the USB. The sound card's the most useful one because a host can read samples from the sound card and then time how long it takes to get a few samples. This will change as the relationship between the two clock crystal changes and allow it to estimate the clock skew. So not only can this affect one computer, but heat travels. So if you have multiple computers, say a few computers in a rack, then one computer can use clock skew to measure the temperature of the other one. And I haven't done this, but I got an email from someone who said that within rack mount servers, it's possible to induce a 3-degree temperature difference on one machine by changing the CPU load on the one below it. For blade servers, where they share their space much more tightly, it might work even better. So 3 degrees isn't very much, but all this graph is 3 degrees as well. And there is some noise in the clock skew measurements, but it's probably less than a degree. Another idea I had, just as I came to the Congress, is on the Sputnik. These have clock crystals too. Maybe it's possible to measure the radio frequency skew and work out whether someone is indoors or outdoors. I don't know if the access points for that can go to that sort of level of detail, but it would be interesting if anyone was able to do that. Okay. So I mentioned an attack on the Tor hidden services, which relies on having some Tor nodes controlled by an attacker. There's a number of these, and they work better and faster when the attacker controls more hosts on the Tor network. There was a very extreme version of that called the Sybil attack, where one person creates a very large number of personas and joins a peer-to-peer network and starts taking over quite a large proportion of the connections going through it. And because Tor is vulnerable to traffic analysis, if the attacker controls the first node and the last node on a connection, then it can find out who is browsing what, which is directly contrary to the goals of Tor. I mentioned that there was a paper that showed that clock skew can act as a fingerprint of the physical host. Also, if we can measure the temperature, then we can guess about the environment. So after I wrote the original version of my paper, there was a small panic on the Tor mailing list because round about 30 Tor nodes appeared over a very small number of days, and this looked suspiciously like a Sybil attack. They were all on the same 2/16s, all in the same ISP. The contact information was bogus. The reverse DNS lookups were all registered on the same day and didn't indicate anything about who they were being run by. And also, when a few people, I think Jacob Applebaum for one, traced back where they came from, it turned out they were very close to Washington, DC, which is home of a fairly large number of 3-letter agencies. So the people on the Tor mailing list with the tinfoil hats got quite upset, and one of my colleagues suggested that maybe clock skew would be able to give a bit more information about what's going on. So I ran the scripts against all these nodes and looked at what I got back. These are 6 of the graphs, and there are 2 things you can tell from this. Firstly, it's each host on each host on a /16 had the same absolute clock skew. That suggests that, or it suggests very strongly that they're all running on the same machine. I was able to confirm this by trying to SSH to one of these Tor servers and seeing what host key I got back, and it was the same for every Tor server. They also made a bit of a mistake, which I hope none of you have made, in that they wanted to prevent people SSHing into one of their servers, which is a good thing to do. So they blocked port 22. But they didn't block port 22 from their own machine. So if you use Tor to connect to their own machine, you're inside the firewall. So the other possibility was that there were different machines but in the same environment, and in which case you would be able to see that it was the same, different absolute clock skew, but the same relative clock skew. But since they appeared to be two physical machines, that wasn't really possible. But we can see some other interesting things in these graphs. This jump here isn't actually a jump in temperature. You can tell because changes in temperature will show up as a curve in the offset graph, whereas here there's quite a tight step. So this suggested some changes in routing behavior. Now, of course, you could find some of this through random normal network management tools like ping, but ping measures round-trip time, which is different. Round-trip time is the time it takes for your packet to go to the host and for it to come back. Now, very commonly, these two paths will not be the same. They won't have the same latency. That's because of something called hot potato routing. Every ISP wants to get rid of the packet as soon as possible because while it's transferring it, it's costing it money. So if a fairly large ISP has presence both in, say, the US and Europe, when the packet is going from Europe to the US, it will be transferred to the other ISP within Europe. When the packet is coming back from the US ISP will try to get rid of it as soon as possible, and it will pass it to an internet exchange in the US. So the path it takes over the Atlantic will be different. The latency measured here, or not so much the latency, but the variance in latency, the jitter, is only from the second half of the path, when it's going from the remote machine to your own machine. So combined with the round-trip time, you can look at one side of the path. And this doesn't require any synchronized clocks, which is the normal way of achieving that. So it's now getting a bit extreme. And I should say I haven't actually tried this, but if you know the temperature of the machine, you might be able to work out its location. ClockSkew only allows you to find out the changes in temperature. It doesn't tell you the absolute temperature. But if you can measure when the start of the day is, when the sun comes up and shines on the computers, and you can also measure the length of the day, because that changes over a long period of time, you can get a very rough idea of the location. Each of these curved vertical lines is the start of the day at each of these locations. And the horizontal lines are the difference in length between 2 days, 6 months apart. And all these numbers are hours. So it takes a long time to get a significant difference. But if you're only trying to work out what side of the equator someone is on, then it might be a reasonable way of doing it. There's going to be problems of things like air conditioning, but in some cases that can be removed, because air conditioning doesn't work on a continuously variable principle. They have thermostats, and when the temperature is too hot, it will turn on, and when the temperature is corrected, it will turn off. If you look at what the pattern this generates, it's a square wave with a varying duty cycle. When it's hot, it's on for a long time, and you'll be able to see the temperature dropping. And when it's off, you'll see the temperature gradually picking up. So along with NTP and problems like air conditioning, it might be still possible to remove these. This attack will work in some cases. It's probably not the best one, but you might still be worried about it and want to defend against this. It's surprisingly hard. You could try to remove timing information. If you block ICMP, then you'll get rid of ICMP timestamps. There's not really any downside from that. Blocking TCP timestamps is more problematic. Not only are they used for protection against wrap sequence numbers, but by estimating the round-trip time, the TCP stacks of modern operating systems will try to increase the number of packets in flight and improve performance. So you'll have some problems with that. If you block initial sequence numbers, then